Hunsaker is a research ecologist with the Pacific Southwest Research Station at the Forest Service in Fresno. She's a scientist that designed and implemented the Kings River Experimental Watersheds starting in 2000. This is the only long-term watershed research in the Sierra Nevada Headwaters. With that, Carolyn, I'll turn it over to you.
I'm going to be presenting today recent findings from the Kings River Experimental Watersheds in the context of questions about forest health and water yield. It's been for a long time recognized that one of the very important functions of forests is to provide water supply and good water quality. It is actually one of the major reasons the Forest Service was established. However, in California, even though about 50% of the Sierra Nevada is in federally managed lands, and much of that is in forests, and the Sierra Nevada provides between 40 and 60% of the surface water use in California. The Sierra Nevada never was able to sustain, through any organizations, long-term studies on the source waters from these forests. So in a little before 2000, the research station of the Forest Service decided to look for a location to do a long-term study on headwater systems in the Sierra Nevada. And that is how the Kings River Experimental Watersheds were started. We selected a location on the Sierra National Forest on the headwaters of the Kings River that was ideal for meeting the objectives of the work that we wanted to carry out. And on this slide, you can see the two research areas outlined in red. There are two sets of 4 watersheds. The lower elevation site, the Providence site, and the high elevation site, the Bull site. The Providence site is between 5,000 and 6,500 feet elevation, and it is a rain and snow mixture of precipitation. The research is also supported by Southern California Edison. Some of the private lands are inside the watersheds are shown in the brown shading color. At the Bull site, it is a snow-dominated area between 7,000 and 8,000 feet elevation. It also contains parts of the watersheds in the Tea Kettle Experimental Forest, and one of the control watersheds in the Tea Kettle Forest has never had roads and never had timber harvest. And so it can serve as truly an example of what unmanaged, undisturbed small watershed is functioning, and is a real advantage because it can then be compared to our other watersheds, which have all had different degrees of management as in national forest lands. So we established and instrumented these 8 watersheds in 2000 and were able to start data collection in 2003. And that gives us a nice long-term set of data to answer several questions. I want to talk about forest restoration and the goals of the Forest Service. Sustainability is really all about balancing. And humans have a set of things you can call ecosystem services. things like water yield, water quality, wood products, the things I have listed on the right that different people place more or less value on. We also want a healthy forest, and those are the things I've listed on the left. We have a goal of reducing wildfire risk, and ways we can do that are through tree thinning and prescribed fire. We want to be sure we maintain good soil health and avoid excessive erosion. We want to improve tree growth so we have more of the mid to larger sized trees and less of the small trees. And we want the forest to be robust for multiple stressors. And in the southern Sierra Nevada, that is especially important because we have a very high stress from ozone and nitrogen deposition in air pollution. So as we talk about something like the role of forests in supplying water for human and ecosystem use, we also have to think about all the other things that are valued that forests supply. The goals of the experimental watershed study were to understand the processes and quantify the variability of these headwater stream ecosystems. They're highly variable. It's a Mediterranean climate, and in the southern Sierra, we get almost no precipitation in the summer months into early fall. We have an applied science question, which is evaluating the effects of forest management for healthy forests. And the treatments that were applied to the watersheds are thinning, which was completed in 2012, and prescribed fire. Two of the watersheds were burned in the fall of 2013. We had planned to burn the other two at the Providence site this month, but because of the high fire risks, we will not be allowed to do that, and hopefully those will be burned in the fall of 2014. And thirdly, to apply models to predict and better understand the processes that we're gathering data on. So the watershed study, in each group of 4 watersheds, one watershed is thinned only, one watershed has prescribed fire with understory burning, one watershed has the combination of thinning and burning, which is the forest restoration approach that is probably needed in much of the mixed conifer in the Sierra Nevada. And then one watershed has nothing, the control watershed. And that allows us to, as we measure attributes in the post-treatment phase, allows us to hopefully attribute any effects, whether they're positive or negative, to whether it was the thinning, whether it was the understory burning, or the combination of both, and feed that information back to managers, which will hopefully help them make more informed decisions about how to manage the forest in the future. We measure a large number of things on these experimental watersheds, and I'm not going to be able to talk about them all today, but I wanted people to see what the suite of things are. As an ecologist, I felt it was very important that if we're looking at forest restoration and the benefits of that, we had measurements that would capture physical properties, chemical properties, and biological properties. And we've been able to succeed to do that. We measure stream flow or hydrology at 10 streams. 8 of those are the experimental ones I've described. We have 4 of our own meteorology stations. As I mentioned, because we have poor air quality in the southern Sierras, we have air quality as one of our measurements. Sedimentation and suspended sediments or turbidity in the streams, soil condition and the geomorphology of the streams, water chemistry in incoming shallow soil and streams, and snow melt. We measure fuel or dead and downed wood. And then our biological measurements are stream macroinvertebrates, which are considered some of the best indicators of water quality in small fishless streams. Stream algae, we have a special study looking at riparian and upland vegetation throughout the experiment, and Yosemite toad. So the primary question on the applied side is, can we do forest restoration and have the results that we desire? So we want to have acceptable short-term effects in the first 1 to 3 years after the treatments. We might expect to have a small decrease in water quality, perhaps a little bit of an effect on soil condition, wildlife habitat for some species. Reduction in fire risk, of course, is a positive, and an increase in water yield or soil water moisture in soils would be a positive. The real goal, however, is the beneficial long-term positive effects in the 5 to 20 years following the treatments. And those ideally will be some degree of an increased water yield or increase in moisture in the soil, improved riparian and meadow ecosystems, the forest being more robust to multiple stressors, and reduced risk of fire. So what I'm going to talk about today, because it's a focus on water yield, water supply, is what we've learned about the water budget in the 13 years we've been gathering data now, flow paths in these small watersheds, and then sediment loads, which is a significant question when you are removing vegetation on forested lands. You don't want to remove so much vegetation that you then create a sediment erosion problem. So there are only a few places that water can be stored in the ecosystem. It can be stored in the soils and deep groundwater. Vegetation is actively using water when the vegetation is growing. We have water in streams and lakes and other surface water bodies, and then in the atmosphere. So the one place that humans can alter the water budget is by how much vegetation we leave on the ground. And so in a forest, when you go in and thin or remove trees and understory brush, then less water is being used by the vegetation and being evapotranspired into the air, and likely more water is then either in the soil or being released into streams, rivers, and lakes. So what have we learned in the pre-treatment phase of the water, about the water budget in these 8 headwater catchments? We've learned that precipitation varies between 30 to 80 inches. It reaches a maximum at 4,000 feet, and then it plateaus out. So even though I have 4 meteorology stations on my study area, the amount of precipitation coming in, they're all above 5,000 feet, is fairly similar across all 4 places that we measure. It's just that in the lower elevations, more comes in as rain or a mix of rain and snow, and in the high elevations, almost all of it comes in as snow, except perhaps an early rainstorm and a late spring rainstorm. The runoff ratio, which is simply dividing the amount that is discharged in the streams by the amount coming in the precipitation, is about a 10% increase per 1,000 feet in the southern Sierras until we hit that plateau level at around 4,000 feet. The snow-dominated watersheds produce 2 to 3 times the discharge of the rain-snow watersheds. Our soils are very similar, although the soils at the higher elevation are somewhat coarser and less developed and therefore drain a little bit more rapidly. But we believe the majority of the higher production of flow in the streams is due to the dominance of the snowpack. The trees at the rain-snow interface are using more water in the winter than we thought. This work is able to be known because of the Southern Sierra Critical Zone Observatory that is co-located at my Providence site. Evapotranspiration being measured by the flux tower there is showing about 80 inches on an annual basis for evapotranspiration. So the trees are growing more even though they're in a cold situation because of the way the snow patterns come in. You get a big snowstorm, it'll almost all melt off, then we'll get another big snowstorm, and so these trees have learned that they continue to grow through the winter and don't really have to shut down the way trees at the higher elevation sites do. So let's take a look from 2004 to 2012 at the amount of annual discharge, this is in cubic meters, coming out of these 8 watersheds that I monitor. The top 3 lines are the three of the snow-dominated watersheds at the higher elevation. And they function in a fairly similar way with that snow dominance. The middle 3 lines are the Providence watersheds, 3 of the Providence watersheds, and they behave in a very similar pattern. And then the 2 lower lines are our 2 smallest watersheds, one in the Bull site and one in the Providence site, and they behave similarly. So there's 3 groupings if you look at annual discharge, and if you divide these by the size of the watersheds, you still see this set of groupings. An interesting thing to note, even though 2012 was a very low precip year, and people are now concerned because we're going into our 3rd year of low precipitation, in 2007 and in 2004, with regards to discharge from these systems, it was very similar to 2012. You can also see that when we have lower precipitation years, the discharge at the middle 3 watersheds is dampened and becomes very similar to what it is at the bottom 2 watersheds. But the 3 very large water-producing watersheds, while they're dampened during those periods, they still are elevated above where the others are. There has been a lot of work over the years on forest vegetation and water yield. If you look in the literature across the United States alone, there have been 95 watershed experiments carried out over the years. And I listed here some of the findings from those studies, and we'll be, of course, comparing what we see from my 4 watersheds that were thinned in 2012 to the findings from previous work, and that is ongoing now. There's also been a modeling exercise by some of the University of California locations with a general conclusion that if you reduced forest cover by 40% of the maximum, you might be able to get as much as a 9% water yield increase. And that would be a pretty severe cutting of forests and is probably not likely to happen. in California or in the Sierra Nevada. And we'll talk about that a little bit later. But it is a modeling prediction that we can look at as perhaps the best one could do if one was trying to simply maximize water yield. These are some preliminary findings from the P301 watershed where we have the most instrumentation. And a water balance is basically looks at the incoming precipitation and the places that can be distributed in the flow going out the stream, in the evapotranspiration that is through the vegetation, and in the soil storage parameters. So these are numbers for 2010, 2011, 2012, and 2013. And you can see how the water is partitioned amongst those four categories as we move from kind of an average year in 2010 to a high precipitation year in 2011. You see us almost doubling the storage in the soils, and then two low precipitation years in 2012 and 2013, where we're actually going deficit on our soil moisture storage. The one thing to note is even though precipitation varies dramatically during that period, the amount of evapotranspiration stays almost constant with somewhat of a reduction in the 2013 period. There are other things that are of interest when one talks about water yield from headwater systems. Because we measure chemistry and a lot of different types of water in the ecosystem, you can do what is called a mixing model and use the chemistry to inform you about what are the primary flow paths in the watersheds. And we did that, and we found that 60% of the stream discharge was dominated by subsurface flow. That's the flow in the upper mineral soils and litter, not in the deep groundwater. Less than 40%, but still a large portion of the flow comes from that snowmelt runoff period in these systems that do have a significant amount of incoming precipitation as snow. And then the smallest proportion, less than 7%, is in the fall storm runoff periods. So that's how the water is moving through these small watersheds. As I mentioned earlier, one has to always be concerned about soil erosion and sedimentation when removing vegetation from the land, especially if your soils are highly erodible and you're on steep slopes. There was not any information on what one could consider the current or historic range of variability in sedimentation from the Southern Sierra watersheds. And we've, over the years, been able to document that, I think, very well. In the picture there, you can see one of our sediment basins in the wintertime. We built these small basins. They slow down the flow at the bottom of my watersheds. We drain them in the summer and dig them out by hand and weigh and characterize the annual sediment loads, and we've done that for all of the years that the watershed has been running. The sediment loads varied from 2 to 17 kilograms per hectare per year. Because we have that one tea kettle watershed that has never been roaded or harvested, we really do have the natural range of variability in a headwater system. and that is really on the same order of magnitude towards the higher numbers of some of the watersheds that have been received forest management in their history. So current range of 2 to 17 kilograms per hectare per year, with the natural range of variability at that 16 plus or minus 21 kilograms per hectare per year. And here's just a graph of that sediment loads with all 8 watersheds displayed here from 2003 to 2009. And then this upper line, the wider line, is the amount of precipitation that came in each of those years. And of course, how much sediment you have is very much influenced by the intensity and the amount of precipitation in that year. So you can see the variability, and then one of our watersheds, the P304 watershed under high precipitation years is certainly the big outlier in the amount of sediment that it carries. So when we talk about how much water can be produced from forests, one needs to think about if you're going, what level of canopy cover, what level of tree density you want out there for your values. And many of the values are things like clean water, scenic, recreational opportunities, good habitat for wildlife. So some of my colleagues, Malcolm North and Jonathan Long and others, have been looking at how much of the national forests in the Sierra Nevada are in trees that could be harvested, and what are the constraints to mechanical harvesting on those landscapes. And I've just listed them here. We have legal constraints like wilderness areas and roadless areas. There are operational constraints. How steep is the slope? Do you have existing roads? And then there are administrative constraints, areas set aside for research natural areas, how close you are to streams and rivers, special needs of wildlife that the public is especially concerned about, like goshawks in California, and California spotted owl. And you start reducing the amount of forested lands down to fairly significantly when you look at the whole set of constraints there are to where you might do mechanical harvesting and how much mechanical harvesting you might do. And that takes us back to where I started out, which is about sustainability, resiliency that you want in your forest ecosystem, and what we're trying to balance between the condition of the forest and the ecosystem services that we're looking to that forest to produce. And that is really why the Kings River Experimental Watershed was set up the way it is, which is to look at the health or condition of the whole ecosystem, the physical characteristics, the chemical characteristics, and the biological characteristics. There's a very nice report by the World Resources Institute done in 2013, and it's called Natural Infrastructure, Investing in Forested Landscapes for Source Water Protection. And if you're interested in this topic, I really recommend this. It's well written for the general audience. It's kind of an engineering approach to describing to people the importance of forests and natural areas in the role of producing water. And so for perhaps the oldest city is New York City, which gets their water from the Adirondack watersheds. And that's actually where The first mistakes were made when the Adirondacks were heavily harvested and all of their soil started coming off their mountains and into their water and the source of water for New York City, and people put two and two together and realized that that intensity of denuding essentially the mountains was not a good thing to do and led to the creation of the Forest Service. So I highly recommend this report to get a nice description of some of the things to take into consideration. And it has several case studies. None of them are in California, but I think one is in Washington State and one in Colorado. I think California is a little slow to be picking up on this whole situation, which is probably a function of the fact that in our state, people are really disconnected from where their water comes from because the state water distribution system is so heavily engineered, and water is being moved around very long distances to people from where it originates. And the final slide, simply, a lot of what I talked about today is summarized in a short paper in Mountain Views, and then much of the information is on my website, which is listed here, and these are just some photographs from the experimental area.